Ну вот вроде уже, да.
Да, все пошло на Ютубе.
Да.
Ну, когда скажете, я могу начать, да?
Да, вы можете начинать.
Ну вот уже рослый уже появился, может начинать.
Сейчас, кто-нибудь просмотрите, пожалуйста, список участников.
Хорошо, вот я вижу Алешу Рослого.
Не, это все, есть Ратауян. So we switch to English because if there is at least one English speaker.
Okay, no problem. My slides are in English anyway.
Okay, so.
If it's possible, well, I suggest to everybody to switch on their camera because, well, you see me, I also would like to see you, right? If it's possible. So thank you for inviting me. You know, I'm generally speaking something like a physicist. So the subject which I'm going to talk about is not so usual for me because I'm doing mostly quantum field theory, things like that. And this subject is purely mathematical. Why I started to study it? Because I was interested, I was doing for several years, for many years, supersymmetric quantum mechanics. And you know that there is a relationship between supersymmetric quantum mechanical systems and just geometry. For example, the RAM complex is the simplest, one of the simplest supersymmetric quantum mechanical systems. I want to show you a kind of book which I've written and which was published this year. So I will switch on. That's the book, right? You know, it's just about the relationship between supersymmetric quantum mechanics and geometry. But what I'm going to talk about today is just geometry without, well, connections with supersymmetry. It's just, well, some geometrical problem. Now, what is this problem? So it's about so-called Hkt manifolds. Maybe it's not so generally known, so everybody knows Keller manifolds, everybody knows hyperkeller manifolds, and that's Hkt manifolds. I will explain what is this. Well, Hkt stands for hyperkeller with torsion. So I will start with just first reminding you some rather well-known facts about geometry. And then about this Hkt, I think that not everybody knows it well. So first, what is a complex manifold? There is a notion of almost complex manifold. So that's written here. It's even dimensional manifold, where the special structure called complex structure exists. That's a tensor, which is antisymmetric, and the square of this tensor gives minus unity tensor, -1. Now the indices are well lowered and lifted by the metric. It's trivial remark for a physicist, but not so trivial remark for mathematicians, because mathematicians often consider, well, the geometry without metric, but I will consider it with metric. So that is called almost complex manifold. And now the complex manifold is basically the manifold where you can introduce complex coordinates. And in this language, so I don't want to use the language of complex coordinates. I want only to use the language of real coordinates. And then in this language, this tensor should satisfy the additional condition. The so-called Nienhuis tensor vanishes. That's how one of the forms where this Nienhuis tensor can be written. Now, probably I will go right now to the blackboard and will show you what is this integrability condition, integrability of what. So I'll just show on the blackboard. So suppose you have a complex coordinate, and there are some real coordinates. And then it's something like that. M, N, there's that. So small n, it well marks complex coordinates, and large n marks real coordinates, right? Now that's the relationship between the two, and that's the equation system for D equations. And so this condition that the Nienhuis tensor vanishes is the condition that this equation is compatible. And then one can also show that once this condition is fulfilled, this equation system has a solution. So these are rather known facts. Now I will show the slides again. So that's complex coordinate. Now I introduce also the metric and also the Filbine. And as usual, the indices A in the beginning of the alphabet, they refer to the tangent space, and in the middle of the alphabet, they refer to just to its Wald indices on the manifold. There's the complex manifold. Now, what is a Cayley manifold? Cayley manifold is a complex manifold where this complex structure tensor is covariantly constant. Is covariantly constant with respect to the usual Lebesgue-Witte connection, or in the physical language, this gamma are Christoffel symbols. I don't know what it is. We are just more used reading, general relativity by Landau-Lifshitz. So there are words, Christoffel symbols, but there are no words Lebesgue-Witte connection, but it's the same. Now, if you have a complex manifold which is not Cayley, then still the complex structure is covariantly constant, but with respect to some class of connections which involve torsion, or which there are also some connections which are torsionless, but then the metric tensor is not covariantly constant. But I will not talk about it today. So I suppose that the metric tensor is covariantly constant, but this connection may include the torsion. So instead of usual Christoffel symbols, I can write some tilde Christoffel symbols which well, include also this second term, and C, L, and K is a torsion tensor. Now, the Christoffel symbol is symmetric under the permutation of N and K, and this tensor is skew symmetric, right? Now, there are many different choices for C such that this condition is satisfied, but some distinguished choice is the choice where this tensor is completely antisymmetric, not only with respect to N and K, but with respect to interchange of all indices. And then this connection with respect to which the complex structure is covariantly constant and the torsion tensor is completely antisymmetric, there is only one such connection, and it's called Bismut connection. Now, there is a beautiful formula which I can show you how this tensor, this torsion tensor, looks like explicitly. So here, these nublers are standard covariant derivatives, Levi-Civita covariant derivatives. If there is zero, these covariant derivatives, then there is no torsion. And if they are not zero, then the torsion is present, right? Okay, that was Kelly manifold and generic complex manifold. Now, what is hyper-Kelly manifold? Hyper-Kelly manifold involves three different complex structures, and they satisfy quaternionic algebra. So if you multiply I by J, you obtain K. If you multiply I squared and J squared and K squared, it's -1. They satisfy quaternionic algebra. And also all these complex structure are integrable. So Nienhuis tensor vanishes for any of such complex structure. Now, a manifold, hyper-Kelly manifold, has the dimension which is an integer multiple of 4, right? One can always choose the coordinates where these complex structures acquire the canonical form. So there may be some different complicated expressions with the Wald indices, but if you write them in the tangent space, then they're diagonal. So they exist in 4x4 blocks. They block diagonal matrices. They're block diagonal matrices. And these blocks, can be chosen in this particular way, right? So they are antisymmetric. All these matrices are antisymmetric, and they're also self-dual. You see the element 1, 2 is the same as 3, 4. And here the element 1, 4 is the same as 2, 3. So they're self-dual, and physicists can recognize in these matrices what is called 't Hooft symbols. They are, they're used in a description, instantons. Okay, now what is Hkt manifold? So it's still the manifold of dimension integer multiple of 4, which involves 3 quaternionic complex structures. And they're not covariantly constant generically with respect to Levi-Civita connection. Then it would be Hkt manifold. But they're covariantly constant with respect to one and the same Bismut connection. One and the same is important restriction because, well, so it's important that the connection with respect to which each of three complex structures is covariantly constant is the same. So they were introduced by physicists, well, some time ago already. And then mathematicians also learned what is it. So Misha Verbitsky, for example, is a great expert in Hkt manifolds, who he works in, how is it called? Well, I've forgotten, but you know, E something. Well, I've forgotten how it's called in English. Anyway.
How in Russian? How in Russian?
In Russian, I also forgotten how it's in Russian. But you know, that's a new institute very strong in mathematics, right?
Do you mean High School of Economics?
Exactly. He works there. Right now, I don't
Excuse
know.
me, may I ask a question concerning this?
Sure.
Since we have such a condition that the same connection is compatible, it's preserves actually, right? The three complex structures, it preserves the whole family, one complex parameter family, right?
You mean that you can write this superposition of this complex structure? Yes.
Yeah, but my question is that may it happen that
who is talking? I don't see you.
May it happen that there exists such a connection which preserves only two but not three structures?
No, because if you can multiply. If you have two complex structures, then you have.
Yes, you always. Yeah, of course. Sorry, it was stupid. Sorry.
Okay. Andrei, unfortunately, you have the light behind you, so I don't see well your face. So you were talking and I didn't see it. Okay, then that doesn't matter. It's not important.
It was not me, it was Alesha Rosly who was asking.
It was Alesha Rosly. Okay, sorry. Okay, anyway. So what is HKT? I already said that, hyperkähler with torsion. But it's not very good name because these manifolds are not hyperkähler. And they're even not Kähler because the complex structure, neither of them is covariantly constant in the usual way. But that's the name attributed to the discoverers. They christened it like that. And so everybody uses it right now. So hyperkähler with torsion. Now, why it's interesting, these hyperkähler manifolds with torsion? So for me, they were interesting because they are related to some interesting supersymmetric quantum mechanical systems, but that I will not talk about today. Also, you know, hyperkähler manifolds, it's rather this condition that the manifold is hyperkähler is rather restrictive condition. And so there are not many hyperkähler manifolds compact. So we know in 4 dimensions some non-compact hyperkähler manifolds, Taub-Nat, Iguchi-Hanson, they're non-compact. And there is only one compact hyperkähler manifold in 4 dimensions, so-called K3, but it's rather complicated.
You forgot also the torus. Two-dimensional
Okay,
complex
that's
torus.
correct. So yes, so you can have flat, well, Euclidean space, and you can, of course, you are right, and you can make 4 circles for torus. For torus, of course, is also hyperkähler. You are right. Now, but it's trivial, and K3 is non-trivial. And with Hkt manifolds, so there are many of them which they are non-trivial. In particular, many group manifolds of dimension integer multiple, which dimension is integer multiple of 4 are Hkt, though not all of them. I will try to explain that later. So Hkt is like hyperkähler light, something like that, right?
Are we talking about compact manifolds?
I will talk about compact group manifolds today, yes.
And for hyperkähler manifolds, there are attempts to classify them. Is there any answer for hyperkähler with torsion?
Well, full classification, you know, there is a full classification of, I don't know about classifying even hyperkähler manifolds of higher dimensions, that I just don't know. Maybe it exists, but if you have, I don't know, 20.
It's a work in progress, how to say.
Work
But
in
it's
progress,
very,
okay. So it even doesn't exist even for full classification, even for hyperkähler manifolds. For Hkt manifolds, also I don't know full classification. I will talk only about group manifolds and homogeneous spaces. And then there is full classification. Maybe not all Hkt manifolds are group manifolds, that I don't know. But those which are group manifolds, that's the only which, well, speaking of a compact manifolds, the only which I know. Non-compact, that's a different story. And that I will talk about, and I will give you the complete classification of those group manifolds which are Hkt. Now, what is the simplest example? It's just 4-dimensional manifold which is conformally flat. So if this conformal factor is 1, then it's just flat space, or as Losha mentioned, 4-dimensional torus. And generically, well, if F is something, then generically it's non-compact, but also some interesting compact manifold with this kind of metric exists. It's called Hopf manifold. So what is it? You choose this conformal factor as x squared, so xn times xn, and then you restrict the absolute value between 1 and 2. And then you identify the points, so along the radius, right? So you say that n and n, the vector n, and 2 times n are the same. N is a unit vector, then the the absolute, the modulus of norm of x is 1, and if x is 2, then it's 2 times n. And so you just identify these points. And so then you obtain what you obtain. You obtain 3 sphere which multiplies 1 sphere, also kind of torus, but generalized torus. Or just SU2 cross U1. So it's the simplest case. That's group manifold, and it's Hkt. Hkt manifolds are characterized by torsion. I will write for you on the blackboard the torsion in this case. So this torsion is something like that. So that's antisymmetric tensor with some coefficient. Well, I don't remember the coefficient now. Okay. Now, that's very old result, Samuelson theorem. It tells that any group manifold of even dimension is complex. So this paper of Samuelson appeared in 1953. That's, well, I was not yet born. That's 1 year before the year of when I was born. Well, he proven it well in some mathematical way, and I will show you how it can be proved in the way which I will use later. So this result, I have forgotten to tell you. This result, this classification and all that is not my result. It's known, but it's known in some mathematical papers, and my role is that when I tried to understand it, I couldn't understand mathematical proofs, and I constructed a proof which I understand. And so there's the new proof of some known fact, which I will talk about, right? So you have a group manifold. Now that's the metric, Killing metric. Suppose that the manifold is kind of round, so it's not only topology, but also it has isometry, which is proper for the corresponding group. So you have the metric, and you can consider the neighborhood of any point of, for example, of unity. And that's how the metric then looks like in the neighborhood of unity. Also, one can write the expression for the field binds. That's how they look like. So I will use very soon these formulas. So that's the theorem. And now how it can be proven. What one should do is just construct the complex structure. This complex structure should be antisymmetric, should square to -1, and also should be integrable so that the Nienhuis tensor must vanish, right? Now, that's the expression for the Nienhuis tensor. And the idea is just to substitute there the explicit expressions for the metric and for the field bind in the neighborhood of 1 or in the neighborhood of any point, actually, right? So you see that there are some derivatives of the complex structures, and you do these derivatives, and then you go to the point x equals to 0, and then you obtain a pure algebraic identity. I will show you it in this slide. This identity, now you see its complex structures already in the flat, in the tangent space, right? And F, ABC are structure constants. They enter here in the metric and in the field binds. And also, when you well differentiate complex structures, you obtain the structure constants. And so that's the basic purely algebraic identity. So the geometric problem is reduced to a purely algebraic problem, right? Which one should solve? I will write this beautiful beautiful relationship on the blackboard. Like that. Okay, so how to find this complex structure? One can construct this complex structure. So the tangent space of, so that's the relationship in the tangent space. So the tangent space of group manifold is just Lie algebra, right? And the complex structure is a linear operator acting in the Lie algebra, right? Now I choose some standard basis in this Lie algebra, Cartan-Weyl basis. So it involves the root vectors, positive and negative root vectors, and also Cartan subalgebra, right? Now, and we define the action on the root vectors like that of this linear operator. So like that, it's most, after all, it's complex structure. Something complex should be there. So it multiplies the root vector by I or minus I, right? And now, if you write, for example, that this root vector is complex, right? And it's some Hermitian operator, let's say take T1 plus I T2. Then this complex structure well, acquire these properties, which I told you, antisymmetric, and it squares to -1.
Excuse me, but
Yes.
if your group is the real split form of some simple group, then the vectors E, the root vectors are real.
Well, no, I just think about, let's take SU2, then it's T1,
Yeah, but
C1 plus
SU2 is a compact form.
Compact,
So
compact.
You take only compact forms of the group.
Compact, yes. Compact
Okay, then I understand. All right.
Incidentally, Losha, it's an interesting problem. How can one generalize all this construction for non-compact groups? I don't know. I didn't do it.
But Samuelson theorem is about any only compact groups. Okay.
Compact groups, okay. Yes, compact.
Yeah, all right, thank you.
It's interesting. I think that one can generalize it to non-compact groups, but I didn't do that. I don't know. Okay, so suppose, okay, so well, for each root vector, you have two Hermitian, generator of the algebra. And also you have the Cartan subalgebra, right? So for root vectors, I defined the action of the complex structure, and then for the Cartan subalgebra, so it must be even dimensional. The group is even dimensional, and so Cartan subalgebra is also even dimensional. So I somehow, split it in pairs, 1, 2, 3, 4, 5, 6, and so on. And so I define the action of my complex structure like that. For the Samuelson theorem, I can split this Cartan subalgebra in an arbitrary way. Now, one can then prove that the I, so that's just the constant matrix. It's not anymore the complex structure tensor, it's just a matrix. And it satisfies, one can show that, it satisfies this algebraic relationship written here. So one can show that maybe to convince you, I will do it in some simple case, right? So I will go to the blackboard again. So suppose that A, so is A, and B is A star, and so they belong to the same root. So, for example, E some alpha is E is A plus E A star, something like that, right? Okay, now it should be 0. Why? And C is arbitrary, right? So you write F A star C, right? Then you write minus E A D E A star E F D E C, and then two other terms I can write them later. So I have written this term and this term, right? Now, by definition, this D should be equal to A star, and E should be equal to A. And then this product A star multiplying A star A is just -1, because the square of this matrix is minus unity matrix. So you obtain, so this -1, A star C, and then you have plus, minus and minus, and then F A star A C. Obviously, that's 0, right? And in this case, two other terms are also 0, just any of them 0 separately. There are some other cases when A and B belong to different roots. Then C can belong to Cartan subalgebra or can belong to some third root, but anyway, it can be proven like that. Okay, again, I go to the slide.
What was proved originally? What was proved by Stevenson originally? The same way, or it was more?
I don't know. Look, there is a, well, in my paper, there is a reference. Well, you can read this paper. Whether it was proven this way or not, I don't know. It's difficult, a little bit difficult for me, unfortunately, to read mathematical papers, right? Чукче не читатель, чукче писатель.
Excuse me, is the left invariant, is the complex structure you've constructed left invariant?
Left invariant, what do you mean by left invariant?
Is it preserved by multiplication by elements of the group?
Well, preserves multiplication by the elements of the group. So what particular formula you think about? So unfortunately, I cannot ask you to write it on the blackboard. So I don't know. Well,
let's skip this.
let's skip this. I just written for you this complex structure, so it's difficult for me.
I think it is one side invariant, but not both sides, of course. If the complex structure is constant in the basis of left invariant vector fields, then it is left invariant. That's all.
Okay, maybe. Now, okay. So it satisfies 4, and that proves the theorem. I haven't proven you completely because one should consider several cases, but in the paper it's proven. So that's about Samuelson theorem. And now what is for HKT? So you should have not one complex structure, but a quaternionic triple of complex structure, right? And so what I will show you is how to find this triple explicitly. So the observation, the only new thing which I observed is that once you have one complex structure I, you can construct 2 other complex structures by acting on I by certain group automorphisms. And so you should, if I is a complex structure which satisfies this well identity, then the complex structure which is obtained by automorphisms of Lie algebra, so omega is some automorphism, it also has the same properties. So it's rather clear that J squared is -1. You just have omega transposed, so omega multiplied by omega, so that gives you 1. So you obtain I squared, it's -1. And also it's antisymmetric, right? Because when you transpose it, you obtain minus the same. And so the problem is reduced to finding the automorphism which makes from I, which I already constructed, J such that this J will anticommute with I. That's enough. So because J squared is -1, I already shown, and so it should anticommute, and then if you multiply I by J, you obtain the third complex structure. Okay. So the fulfillment of this condition, it's also important that it should not any automorphism, but well, any automorphism, but if it group automorphism, so the structure constants are invariant. And so that's why this relationship, which is on the blackboard, still is valid. Okay, so how to find?
Sorry, before we went too far, I've got a question about the previous.
Sure.
The Bismut connection exists for any complex manifold or something like this. You mentioned, right?
Bismut connection is well, with respect to which complex structure is covariantly.
In the previous chapter of your talk.
Yes.
You described the complex structure on the group manifold. Is the Bismut connection on for this case? Can we describe it?
Well, okay, that I forgotten to tell you. So it has torsion, and the torsion is exactly the structure constant.
Okay, okay.
So you multiply FABC by
The connection itself can be described. Can it be described explicitly? The connection.
Well, of course, I to tell you that the torsion, well, Bismut
you
connection.
mean that?
Bismut
Okay,
connection, usual Christoffel tensor plus the term with torsion, right? And the torsion tensor.
But I wouldn't call it explicit description. But all right.
Why you wouldn't call it explicit description? It's just a formula. The formula for I don't know, for modified Christoffel symbols. I know that mathematicians call connection always covariant derivative, right? And well, let's call connection the stuff.
For example, do you know the holonomy group of this connection?
Holonomy group for
the Bismut connection.
Yes, I know.
And what it is?
Hkt manifold, it's symplectic group. So, you know, hyperkelly manifold is the manifold where holonomy group is symplectic for usual standard connections, right? And for Hkt...
It's contained in...
Stop. What?
In general, it is contained in the symplectic group, not the whole group.
That's true.
For example, in the flat case.
That's true. It can be like, it can be smaller. That's true. And so, but for generic hyperkelly manifold, it's symplectic group, SP of n, where the dimension is 4n, right? And so for Hkt manifold, the same is true, but not for the usual symmetric connection, but for this Bismut connection with torsion. It's also symplectic or maybe smaller, right?
I see. Okay, thank you.
Okay. So how to construct this triple? Consider the simplest case, 4-dimensional. So there is only one root vector. And so the I already defined, it's like that. So in the following, so when it's beautiful letter, that's a matrix 4×4. And the complex structures in higher dimensional case will be denoted by straight letters, right? But that's calligraphic, well, EU calligraphic, European calligraphic, I don't know what is it. Anyway, special font, that's 4×4 matrix. So the first two, these elements, 1, 2, and 2, 1, it follows from this definition, which I've chosen this, I like that. And then our algebra involves the third generator, Cartan subalgebra, which has two generators, the Cartan subalgebra of SU2 and then U1 also, T3 and T0. And so I define it in the same way as, well, I already written here, right? Okay, now the automorphism which makes from this beautiful I, beautiful J, is like this. This is the automorphism. So, you know, E plus plus E minus is what is called sigma 1 by physicists. Symmetric matrix, and if you apply to any generator this transformation, conjugation, then you obtain some other generator, and what you obtain, if it's T1, then nothing has changed, because E plus plus E minus is just T1. exactly. Should I switch off the slides when I show you on the blackboard? You don't see blackboards otherwise, right?
Of course, we cannot see both simultaneously.
Okay. Then I'm doing correcting thing. And so the generators 1 and 0 are not transformed, and 2 and 3 are changing the places, and there is also minus. So you obtain this matrix. And this matrix is one of the matrices, one of the Hkt symbols which I shown you before, right? So it's self-dual, and it anti-commutes with I. And so the third matrix can be obtained as a product. So this letter with this beautiful rounding downstairs in the bottom is J, right? So that's beautiful I and that's beautiful J. And so you obtain beautiful K. That's the third matrix from the triple which I wrote for you. And also it can be also obtained from this I by a certain automorphism. So E plus minus a minus, that's I sigma 2, right? And so that's quaternionic, that's
excuse me, does it mean that you have two automorphisms, right? One for
yes.
beautiful J, and the other for beautiful K, right?
Yes.
But what is the algebra of this automorphism? Something like the groups Z3 or what?
Algebra. So if you apply again, each automorphism squared.
Yeah, what is the product of two automorphisms? It is identity?
Product of two, one moment. No, it's not identity. The automorphism which makes J from I also makes K from J. So one moment.
The same one.
It's
I don't know.
So isn't it a kind of
good question, Losha? Cannot answer you right now. Just I'm thinking. So
you probably say that the second automorphism is the square of the first one.
Maybe. So one should write several lines for that.
If you don't know, you don't know. Okay.
One should write several lines for that, and then it can be found out. I have never written those lines. I'm sorry. Okay, now the already non-trivial example, SU3. So it's a-dimensional manifold, and it's HKT. There are three roots, two simple roots, and the structure of the roots is schematically shown here, right? And this alpha plus beta is the highest root, right? And alpha and beta are simple roots. Now for each root, so that's 1, 2, right? Alpha is T1 plus IT2. So you do the same as for SU2, and you define that I21 is equal to minus I12 is equal to 1. And you do the same for beta and also for alpha plus beta. Beta is 7 and 6, and alpha plus beta is 4 and 5, right? Now, the Cartan subalgebra is two-dimensional here. So, well, it's two-dimensional, it's rank 2. And it's convenient for me to choose not quite standard basis. So usually in physics applications, you choose P3, which is in the left upper corner. and T8 is diagonal here, 1, 1, and -2, right? And I choose it in a different way. I choose the T3, which is, well, a partner of the root vectors alpha plus beta, right? So the partner of the highest root. So that's the core root, which corresponds to the highest root of our SU3 algebra. And T8, I choose orthogonal, so it's not 1, 1, -2, but 1, 1, 1, -2, 1. So for SU3, you can choose it any way, and so it works anywhere. But to generalize this construction to an arbitrary group, it's important that I pick up the highest root, and I pick up the core root, which corresponds to this highest root. Okay, and then you already defined your matrix for 1, 2, 4, 5, 6, 7, and that's for 3 and 8. Now you can observe that this 8 by 8 matrix splits in 2 4 by 2 blocks, right? The first block is in the subspace 4 and 5, that's the highest root, and then 3, 8, that's the Cartan subalgebra. So it's like, you see, you choose the subgroup SU2 cross U1, or subalgebra SU2 plus U1, right? And the construction is the same as in the simplest case, SU2. In the terms of algebra, SU2 plus U1, right? And then there is second block, which acts on the root vectors alpha and beta. And so these blocks are independent. So our complex structure I has a block diagonal structure. And each block is this beautiful I, which I have written before. Okay, so I constructed, and now the automorphism to construct J. And so again, I take the highest root vectors, and that's the automorphism which I choose. And this automorphism, it acts in exactly the same way as in the simplest case for the block highest root plus Cartan subalgebra, right? And so you obtain this calligraphic J, right? And also one can observe that you obtain the same in this second block. You also obtain the matrix J. So you just look how this automorphism, right, acts on the root vectors EA, E minus, E alpha, E minus alpha, E beta, and E minus beta. And you see that it's the same, it's also the same block. And so it anticommutes with I, and this third complex structure is obtained by the product of I and J, or by a similar automorphism, but where you have not the sum of the root vectors, but it's the difference of root vectors. That's how you obtain the quaternion triple for SU3. Now, before going to general case, I first explain you how can you do it for unitary groups, and then for arbitrary group, right? Suppose you have this group SU4 times U1, so it's 16-dimensional already, right? You have 6 roots and 3 simple roots and 6 roots, right? That's the highest root. So the basis, so the complex structure I, you define for all root vectors as I well shown, and then to define it, its action on the Cartman subalgebra, I choose some particular basis. So I start with the core root of this highest root, and I call it T out, right? Now, once this highest root is chosen, then you can consider the stabilizer of this highest root. And that's its SU2, this internal SU2, this SU2, right? 3 stars and 1 beta. And this subalgebra also has its highest root, which is beta, right? And so its core root I also take as a basis. And then there are 2 generators of the Cartman subalgebra left. The one, I can call it T15, so which is diagonal, which is, well, in the projection to this inner block, it's just a minus unity. In the projection to the outer block, it's plus unity. And T0 is just the generator of U1. And so that's the matrix I for the root vectors in the same way as before, and that's for the Cartman subalgebra. And this matrix also, you can observe that it has block diagonal form. There are 4 blocks now. The outer block, which includes the highest root, its highest root vectors, its core root, and one of for example, T15, it doesn't matter. Then there is internal block, which involves the root E, this inner root, beta E plus minus beta, and the corresponding core root, beta check, right? And the element of the subalgebra, Cartman subalgebra, which is left, there is T0. That's 2 blocks. And then there are blocks which involve only root vectors. One block involves this root vector, alpha plus beta, and gamma. And another block involves alpha and beta plus gamma. One can check explicitly that, that's for I, that's clear. It's not quite trivial when we will act on certain automorphism, so that the matrix which we obtain is also block diagonal. But for the matrix I, it's trivial because it's block diagonal with blocks 2 by 2, not necessarily 4 by 4, right? Now the automorphism also involves the highest root here. That's important. And then one can observe that this automorphism converts calligraphic I to calligraphic J in the block, outer block, and in the block 3 and 4. And it doesn't do anything, it just doesn't act on the generators in the second block. Second block is left unchanged. So you don't obtain what you want. You obtain some matrix which is J, calligraphic J in 3 blocks, and calligraphic I in the 4th block, which remains. But you can apply another automorphism, the inner automorphism, which converts I to j in the inner block and doesn't act on the generators of 3 outer blocks. So it's like that. And so it doesn't act on the outer blocks, and so it converts I to j, and you obtain the block diagonal matrix with j in any block, any 4x4 block. So you can do it for any unitary group. So that's the procedure. Take the highest root, consider the centralizer of this highest root. Now I will draw for you some picture. So that's the Binkin diagram of what there's already SU5, right? And that's the highest root. It's like that. This highest root is orthogonal to these roots, alpha, beta, gamma, delta. Is orthogonal to alpha, beta, and gamma, and it's connected like that with alpha and delta. And so the centralizer, it was stabilizer, I don't know, centralizer, stabilizer, it's not the same thing, but it's difficult for me to distinguish between them. Anyway, the subalgebra, which is invariant, which is left intact, is subalgebra generated by beta and gamma, right? It commutes with the highest root. And so you see that that's SU3, right? You had SU5, and so the stabilizer is SU3. Okay, then generically, you have, if you started with, for example, SU5, n equals 2, you obtain SU to n minus 1. Now, take the highest root there and do the same. So you apply the automorphism, which acts on the outer blocks, and then you obtain, if the group was large, then the centralizer is also large, right? And so you pick up highest root there in the centralizer, right? And then you repeat the procedure. You write the automorphism, which converts I to j in this outer blocks of this centralizer. If this highest root in this centralizer still has non-trivial centralizer, then you repeat the process. And so you may call the whole set of all these higher roots and these consequent centralizers basic roots, and corresponding coroots, basic coroots. And note that for unitary group, for this group, or for this group, the number of these basic coroots is just half of the dimension of the Cartan subalgebra. For example, for SU5, you had 2 blocks. SU, one moment. For SU3, right? You had SU3. You had no, for SU3 it just converted everything. You had only one highest coroot, and then the one element of Cartan subalgebra which is left, and 1 plus 1 makes 2. And for example, for SU5, you had the outer highest root and then the inner highest root, right? Like here, this beta plus gamma, right? On the blackboard. Okay, and then, but the dimension of the Cartan subalgebra for SU5 is 4. So you have 4 these coroots which participate in the blocks together with root vectors. And you have also some 2 other elements of Cartan subalgebra which also are used in other blocks. So it's important that their number is the same. And so you construct first one complex structure and apply a chain of automorphisms for all these higher roots. And so the resulting matrix anti-commutes with I, and you are done. You obtain your triple. Now, what to do in arbitrary group? You do basically the same. The complication for an arbitrary group is that the centralizer can include several non-abelian factors. The centralizer of the highest root in unitary group was also in unitary group, only one non-abelian factor. And for an arbitrary group, you can have several of them. Again, I will draw for you a picture. So that's the Beaton diagram for SU5. Right? And then I can consider spin 7. And then you have, always forget, 2 long roots and 1 short root, right? And the highest root is here. And it's related to the central group. So it's alpha, beta, gamma, simple roots, and that's the highest root. And so it's related to only to beta, and it's orthogonal to alpha and gamma. And that means that the centralizer that's SU2, so in terms of algebra plus SU2, right? 2 factors. So what should you do? You take highest root there, and then you take highest roots in every such factor. And so you obtain 3 basic roots. And so you miss something you cannot construct, but it's not, it's not surprising because the dimension of spin 7 is 21. And of course, if dimension is 21, it's not, it cannot be Hkt manifold. So you can add 3 U1 factors to make it the dimension 24. And also when you add 3 extra U1 factors, then the Cartan subalgebra of such group is already 6-dimensional. And so you can make your construction. So
why you want to add 3 factors? 1 is enough to get it. Oh, it should be divisible by 4. Though.
It should be divisible by 4, and also that's not it's necessary but not sufficient that the dimension is divisible by 4. You also should require that the number of all these basic roots is half the dimension of the Cartan subalgebra. That you should require. Otherwise, this construction doesn't work. So I will show what happens in the case of spin 8, right? So that's the linking diagram for simple roots, and here is the highest root, right? And so you see that the centralizer is SU2 plus SU2 plus SU2. So there are 3 plus or 1 plus 3 basic roots or roots, right? And so that's all, because you don't have anything else in the Cartan subalgebra, and you cannot do your construction. You need another 4 elements to serve all the blocks in your matrix. So you cannot do that. This manifold spin 8 is not Hkt. But if you add 4 U1 factors, then it's okay. So spin 8 is not Hkt. That it's already written in the slide. But spin 8, and 4 U1 factor is already Hkt. So the procedure is the same. Pick up the highest root, consider the centralizer, take all the high, if there are several, if it's not simple, then take all highest root there. Then consider the centralizer of the whole set of this highest root which you obtain on the second stage. If it's non-trivial, pick up highest root there and continue the process. And so the matrix, I just explained why you need it. It involves the blocks which involve highest root, highest co-root, and something else which you need to have, something else from the Cartan subalgebra. If you don't have it, so, well, tang P, so that doesn't work. For SO8 or spin 8, it doesn't work, but if you add 4 extra U1 factors, then it works. So that gives you the question of Igor, the list of all group manifolds. It's known. Unitary.
Is it true that your argument somehow coincides that if you count just dimensions, then for even SO, this SO8, its dimension is divisible by 4 sort of accidentally?
I don't know, it's divisible by 4, maybe accidentally. What it may mean? It's 8 times 7.
SO2L is not the dimension of SO2L is not divisible by 4 at any L.
Yes, of course, SO6 has dimension.
Yeah. If you add this enough U1 factors, then it becomes divisible by 4 at any L.
One moment. The SO and then 8 or 4 or 8 or 12, then it's divisible by 4, right? SO8, 8 times 7 divided, so it's 28, right? For SO6, you have just odd dimension, it's 15. For SO10, you have also odd dimension, it's 45.
No, I'm just asking, did I make a reasonable exercise? I just took a dimension of SO to L at arbitrary L. And
yes,
then just looked how many U1 factors you should add to make it divisible by 4 at any L. Does it give your
that's what is written here. SO for L and SO, one moment. What is,
So I don't see how many factors you need for SO for L.
let me tell you. Well, but it's easy to say. Let's say L is equal to 1, right? Then it's SO6, right? So the dimension is 15, right? So I think you need just one factor. Let me check to be sure. So sorry, this table. So I think it's only one. One moment. I'm just looking for this form, this table in my paper. And where is it? Yes, I see. Okay, no. You should have, well, it's not sufficient condition that the dimension is integer multiple of 4. To make it HKT, then in this case, you need 2L minus 1 U1 factors. So for SO6, it's the same as SU4, you need just one factor. For SU10, you need 3 factors. So for SO10, the dimension is what, 45. You add 3, you obtain 48. So it's divisible, right? But for larger L, you need many factors because you need that the Cartan subalgebra is a rather large dimension, so that it should be twice the number of all these basic co-roots. Now let me say, it's not written here for E6 of you need have 2 U1 factor. For E7, you need to have 7 U1 factors, and here it's 8. Okay, here it's 8.
Andrei, on each of these group manifolds, there is a triple of complex structures. Is it unique? Because in your construction, there were always some choice of bases, which is not unique. So,
well, there are many such triples. I just construct explicitly one possible triple, but there are many triples.
So on each of the manifold, there are many. How many?
Well, they're all equivalent, let's say. How
equivalent
many?
In what sense?
Equivalent in what sense? I think they're equivalent if you just, for example, for SU3 that I looked, you may, it's not enough, it's not necessary to take the highest root in the construction, but you can take the, how many I cannot say you, but they are different. You can take for SU3, right? You can start with this root, right? You can, it's not necessary to take E alpha plus beta, but you can take any root. But any root can be presented as the highest root if your choice of simple roots involves positive and negative, right? So in this sense, it's equivalent. Alpha is also a highest root if you take as simple roots alpha plus beta and minus beta. In this sense, they're equivalent, right?
see usually the existence of hyperkähler structure is very rigid and hard to find manifolds with having such a structure. Now you are saying that maybe this structure, hyperkähler with torsion, is not rigid enough. So what?
It's not.
Nothing can be said about a manifold having such a structure.
It's
Why
not
we should
so
be?
rigid. You're right. Yes.
Why we should be interested at all in such a structure? Besides that, they appear in some supersymmetric computations. I'm just asking as very pragmatical from a mathematical point of view, why this structure is interesting.
Well, the answer should be like that. If there is some connection to some other branches of mathematics or physics, right? These structures are interested, which have some interesting connections. I think you should agree. Now, I was mainly interested in the connections with supersymmetric quantum mechanics. And other connections that you should ask mathematicians, you should ask Misha Verbitsky.
You ask him?
Well, look, he's not here. He doesn't participate.
Oh, you are not here as well. But
he is not a participant in the seminar. I don't see the screen with Misha Verbitsky in this, so I cannot ask him right now. Why is it interesting? I don't know. He has written some reviews about that. That's the structure which interests him for some special reason. And my way to get to that's through supersymmetry. And I can tell you what is the relationship with supersymmetry, but that should be, not today, right?
Of course. No, what is my concern that if this structure is, even for given manifold, there are too many such structures. So,
well, the answer to your question, I answered. For SU3, well, first of all, there is a freedom with this.
are there automorphisms of manifolds that transform one family to another, or what?
Let's see. First of all, there is a freedom in choosing the elements in Cartan subalgebra. So in this my construction, which actually is similar to the construction of mathematicians, I just formulated in some different, a little bit different terms, which I understand better. But this construction is similar. Construction of I is similar to the construction which which was used in the original papers. So there is freedom in choosing the elements of Cartan subalgebra. If you pick up the highest root here, then there are two elements, as I say, two elements. No, if you pick for SU3, there is no such freedom. For SU4 cross U1, there is already freedom because there are two extra elements of Cartan subalgebra which are left, and you can put them in some blocks in some. There is some freedom in this way. Now here, I've chosen this highest root. I told you, but you can choose the root E alpha. And then you can repeat this construction, but only you should present this E alpha as the highest root as a sum of the root alpha plus beta and minus beta. This picture of the roots is symmetric, right? It has Z3 symmetry or something. There are three roots, there is Z3 symmetry. You can consider this root as a highest root, based on two roots here, but one of them should be negative. and that gives you some other complex structures, right? And they are, I think, equivalent because there is, well, I don't know well mathematical terms, but kind of automorphism of one description to another description. So sorry that I cannot answer in more precise terms.
Let me put more precise question. You have a complex structure on unitary group, standard complex structure. Is it
What is
one
standard?
of the, sorry?
What is standard?
It's a complex group, just as a complex.
Yes, yes, but I shown you how this complex structure is built up. You should start with picking up some root, which I chosen to be the highest.
So it is one of the complex structures you constructed, or your complex structures are deformation, or are they equivalent to the standard one? Is there?
Well, if you call standard the one which I constructed, then
No,
I tell you.
I'm just asking. I have SUM. It's a complex structure of the standard. It's a complex group. It has a complex structure.
Well, it has, but if for any complex manifold, the choice of complex structures, of course, is not unique.
No, that's I'm asking. Your family of structures,
yes,
does it contain the standard one, or they're all different?
Well, again, saying standard, you should refer to some special construction, right? Special construction of this complex structure.
Standard definition SUN is not complex. Yeah. For example, SU2 is three-dimensional, so not complex.
Well, of course, but SU2 cross U1 is always...
Yes, yeah, no. You give construction which is not canonical, it depends on some choices.
That's what I'm saying also.
Yes,
yeah, thank you.
Maybe it's too eager.
So if you ask the question, the classification of all possible complex structures, I didn't pose this question, so and I cannot answer, but certainly there are many. There are many possible choices. Okay, so the last subject which I want to cover is homogeneous spaces, the cosets, right? They're also HKT. Many of them are also HKT. And the simplest example is the coset SU4 factorized over SU2. So the dimension is 12, 15 minus 3. And this factorization, it just eliminates, the internal block in SU4, right? So you just factorize over this subgroup. And so this subgroup is eliminated, it just shrinks to 1. And then this 12-dimensional manifold, you construct your complex structure I. It has only 3 blocks, 4x4 blocks, not 4. And what I call automorphism, this one converts this I to J, and this, if you have minus E alpha plus beta plus gamma minus this E, then you obtain K. So this is even easier, to construct the triple of complex structure for this homogeneous space than to construct it for SU4 cross U1, because you factorized and you have just explicitly 3 blocks, and you are done. And so also in some generic case, you may factorize your group over its centralizer over the centralizer of the highest roots. And you can do it in many different ways. And that was done, the complete classification of the homogeneous spaces which admit Hkt structures was given a long time ago in this paper. So again, so my job was, my role is only, it's another proof, which I think is rather simple, of known facts. That's what I did here.
It's time to questions.
Of course, of course.
First of all, when you consider group manifolds, you edit some U1 factors. If I didn't miss, it was always U1 factors, right?
Yes.
But what if you take two group manifolds, take their direct product?
Of course, you can do that. But then if you had not simple group right from the beginning, you can have it. Then you should.
No. I mean, when you see that the dimension of some simple group manifold is not divisible by 4, you edit U1 factors. But if you add another simple group manifolds, can you construct an Hkt structure which is not direct product?
Which is not direct product. That I don't. Well, the group
the same as you did with U1 factors, but with non-abelian factors.
So, Losha, if you have not semi-simple group right from the beginning, there are many not simple semi-simple groups which are also Hkt, right?
Without adding U1 factor, so always with U1.
Not always, even semi-simple, if you have SU odd of SU3, SU5, etc., they're just Hkt without adding anything. And you can add, well, right?
You listed simple groups. I didn't get.
I listed only semi-simple groups. Semi-simple is the groups which
semi-simple is product of simple ones.
Semi-simple, right? By definition, is a group which in this product involves only one non-abelian factor and many abelian factors, and abelian are only U1.
These are reductible. These are called reductible.
Well, it depends on the definition. I looked in the Wikipedia.
Anyway, but I'm saying, for example, if you take, I don't know, SUN times S or K with some particular N and K's in such a way that the dimension will be, the total dimension will be divisible by 4, can you construct an Hkt?
No, because again, then you have many basic roots, and this condition that the number of basic roots, or this chain of the highest roots, the number of the elements in this chain of highest roots should be 1/2 of the dimension of the Cartan subalgebra.
So the answer is no, yeah?
Yes, the answer is no. So, well, you can have, for example, SU3 cross SU3, then you can have, this you can have.
And a structure which is not a direct product structure, right?
I don't know the structure which is direct product. So SU3 cross SU5 or cross SU7.
I see. Without U1s.
Without U1s.
Okay.
Then you can do that, yes.
Okay, that's the answer to my question. Another question is that you started when you turned to homogeneous spaces, you started from SU4 over SU2, right? But
yes.
What about homogeneous spaces like projective space? Which is SU, SUN plus 1 over SUN.
Projective space. But let's think. SU3 cross SU2, so C2, right? The simplest possible, right?
Yeah.
Maybe it works. No, it doesn't work, because when you factorize over U1, then you deprive yourself of the element which you need in the construction. So CP2.
Don't factorize. Take some. I mean, it can be bigger, a little bit bigger than as the projective space.
So CP2 is not HKT. That I can say.
But CP2 with some addition, maybe some bundle over CP2.
Yes, no? If you add, well, how many factors? You need 4 U1 factors, then it would be too much, Yosha.
But direct products factors or circle bundle over CP2?
I know only the construction with direct products. So if you are interested, look in my paper.
Some Grassmannians, maybe Grassmann manifolds. For example, the famous Grassmannian of 2-dimensional place in the 4-dimensional space.
So look, CP2 I know. It says U3 cross SU2 cross U1, and it's not HKT. Now, what you propose,
the Grassmannian of 2-dimensional subspaces in a 4-dimensional space. Just for curiosity, I mean, it's distinguished.
Grassmannian is also, one moment, Grassmannian is also some unitary group divided by the product of unitary groups. So right. It's what group divided by what?
It's like SU4 over SU2 times SU2 times U1, but not exactly, you know, up to some discrete subgroups.
SU2
times SU2 times U1.
I think it wouldn't work. So what is the dimension? 1 month. It's 12, so it's 8-dimensional, right?
8 real dimensions, right?
8 real dimensions. I'm not sure, Losha, and just the whole list of all possibilities is in this paper, in this
a complete list. I see.
Complete list,
okay.
But it's huge. You see, the list of semi-simple groups is not huge, but the list of all homogeneous spaces is huge. But it's there. There is a table of all possible homogeneous spaces in this paper.
Okay. Thank you.
Okay. An example of HKT manifold, which is not homogeneous space.
Just group manifold is not homogeneous space. Homogeneous space is group manifold factorized on some other group, right?
Andrei, but take the other group to be the trivial one.
Take group to be unity. Yeah. Then
okay. So I don't know. I don't know. Even the question.
I think this is a question to Verbitsky. The compact non-homogeneous spaces should be some complicated matter, I guess.
Well, okay. So there was a question whether you need to have a group manifold to be at HKT. The answer is not. It can be homogeneous space. The question whether you need to have either a group manifold or a homogeneous space to be HKT. I guess yes, but I'm not sure. I guess the answer is positive, but I'm not sure. There are clever people, mathematicians, whom you should.
But probably you can, for example, you can find the dimension of the infinitesimal deformations of the HKT structure and compare it to the dimension of those who come from your construction.
K3 surfaces provide an example.
What are you saying? I'm sorry.
K3 surfaces. Probably they're hyperkähler.
What surfaces once more?
K3.
K3.
Yeah.
K3 is hyperkähler.
Not homogeneous, I think.
And not homogeneous.
Yeah, but
yes,
it is not considered as a particular
SU3 is
case.
also not homogeneous in this. One moment.
About SU3.
Okay,
Maybe I
okay.
disagree.
Okay, K3 has nothing to do with groups. Okay, that's then that's the answer. If K3 has nothing to do with groups, then it's hyperkähler, and of course, at the same time, it's HKT. Okay, so then there are examples of HKT which are not related to any group, so they're cosets. Okay.
But may I ask you again, maybe a stupid question, but as concerns the theory, so the product of U1 factors,
yes,
with no non-abelian factors, then the HKT will be always reduced to hyperkähler, or I mean zero torsion, or not? Not necessarily.
Well, I don't understand. If you have four-dimensional torus, it's hyperkähler. It's like flat.
Yes, but does there exist an HKT structure with non-zero torsion? Or it does not?
So it's the question whether there exists HKT structure on the flat Euclidean space.
Yes. Maybe with, I don't know, maybe with some deformation. I don't know, it's a question.
Well, my guess is not, because I never heard about it. Well, that's good for me. That's good for me that there is such discussion, because you ask questions which I never asked myself, for example. That's good for me. So this particular question, if you have just flat four-dimensional...
Just product of S1s.
Well, product of S1, so R4 is the same, more or less.
More or less, yes.
There is no difference. So let's think about R4. Can you define there some connection with torsion? Now, look, the triple of complex structures should be the same, because in 4 dimensions you don't have a freedom. You don't have a freedom. You have your complex structures. Now they are constant. They're constant.
No, if they are constant, everything is defined, I guess.
Yes, it's difficult for me to think about. You can.
Probably you cannot answer immediately, because first of all, it depends on whether we take the metric to be the flat one, or we allow for some curved metric. If the metric is flat, probably there is no much freedom. I don't know. Okay, anyway, Andrei, I'm sorry, maybe the question was not
Losha,
good enough.
That you ask, and you in Igor and others ask questions, that's good. But let me ask in my turn the question to you, which I already mentioned. It would be, I think, interesting to generalize all this construction to non-compact groups.
Maybe, yes.
It would be interesting. And that's some problem which is not solved yet. I told you about the problem which was solved by mathematicians some years ago, and they only considered.
I would start from complex groups. So the situation when one complex structure is already there, and ask myself if there exists J.
Yes. What about even dimensional non-compact group?
Yes.
How to construct a complex structure there?
Yeah.
That's first possible question. I agree with you.
Yes. Yeah.
So maybe if you think about that, then I would appreciate, and we can discuss it.
It's not so easy.
Well, that's true. Science is not so easy.
Okay, I'm afraid that we have to stop the discussion because it's time to.
Yes, it's already 2 hours, Bill.
Yeah.
Okay.
Okay. So just thanks, Andrei, once again for your talk, and we finish our seminar. Thanks again.
Okay, thank you, Igor and Andrei and Losha and all others.
Спасибо.
Thank you.
Спасибо.
Thank you.
Спасибо.
Thank you.
Okay.